So, hi guys, this is Dr. Edwards again. Um, this presentation, I'm taking it from Davis Griffith's book, Quantum Mechanics. So here I'm going to introduce you to this important Dirac notation. So questions come immediately. Now we have addressed the problem of the infinite square well, which is a continuous position space, continuous momentum space as well, where the particle exists. We've the harmonic oscillator, we've considered the harmonic oscillator, where once again a continuous position space exists and a corresponding continual momentum space exists. And that's fine for that type problem. There are other problems now where you will find that the particle or some aspect of the particle, let me go on and put the word spin out there. The spin of the particle and also the angular momentum of the particle in some cases is very much quantized, or discrete is a better word. There's one or two cases, two or three cases, two, three, or four cases, always two or more. And the problem now is to understand the quantum mechanics when the particle can be in one or two states, or somewhat in both of those states simultaneously, which seems a little strange to the mind. But that seems to be the way quantum exists with the superposition theorem. And the Dirac notation is ideal for describing this type behavior. So let me get started. So in an analogous way, remember the unit vectors from Euclidean space, where the ith unit vector is the unit component, or I dot A, in the x direction gives you the x component of a vector A, and similarly for y, and similarly for z, if z is there. No problem. So you've seen this type picture before, where you have some vector, and you can talk about the x component of the vector and the y component of the vector. They both exist simultaneously. You can talk about this vector in two different coordinate systems, the x and y and the x prime, y prime. No problem. You've seen that kind of behavior. Now, what you may have not seen is this structured here. A vertical line and the greater than symbol with something in between. And that is what we're going to call a ket, K-E-T. So the ket now become analogous to unit vectors I, J, and K. The kets exist in what we call Hilbert space, which is a complex number space as needed, whereas I, J, and K always exist in regular Euclidean space. Even the regular space that we live in is a Euclidean space. So why will we do this? So here's this wave function that we've been talking about. It is related to this new structure that we're trying to give meaning to. If you sandwich a bra, this when it's pointing, when you have the greater than arrow, say pointing to the right with the vertical, that's called a bra, B-R-A. And you sandwich that with the ket. This this structure here with the x coordinate is equivalent to the wave function. So what Dirac began to think about is that while we've been doing this less than, greater than in taking the average value, you can separate these two and give meaning to each of them individually. Let me go on. Now, so this is the way you can express the wave function. This requires Fourier integrals. I'm not going to require that, but that's what that is. This is a Fourier integral that converts the wave function in momentum space to the wave function in position space. And this is now the superposition that we've already talked about, that when you add several wave functions, you get the final wave function. Go on and on. Now then, so here we come to this kind of structure. That if you have an operator, so operators are going to be these two-dimensional, you will find them as being two-dimensional matrices. And the cats and the bras are going to be single column matrices or single row matrices. You will find that. And then the quantity that operates or that provides a connection between any two of them will be these matrices, and we call them operators. Okay, let me go on. Here's an example. You will find then that just as you could have that the unit vector I is this matrix 1, 0, and the unit vector J in Euclidean space could be this matrix 0, 1. We can also go on and let this be the simplest way of representing the cat in this Euclidean space. These two are orthogonal. If you now take the inner product of cat 1 with cat 2, you will get 0. But if you take it with itself, you get 1. That is a clear indication that you have discrete orthogonal unit vectors. Let's go on. So then, we just like we had to normalize previously the continuous wave function, you will also normalize these superposition. Like this now represents a superposition of cat 1 and cat 2, which really can be written as this matrix A and B, where A and B are complex numbers. In some cases, they are real numbers, but they are known. And then this then is some type operator, which is a Hamiltonian, which is a square matrix. All of the operators you will see will be square matrices. So now this is the additional way that you can write the Schrodinger equation. I h bar ddt of now you operating on this cat is equal to the Hamiltonian operating on that same cat. All right. So this is some other behavior that you can also represent it in a different space. All that's going on there. Now, so let me skip over here and give you this. So I'm going to eventually give you this homework problem. I'm going to go on and assign it to you. And this is one of the last important problems in this class. And then I'm going to, after we work on this problem a great deal, give you add-in spins. Once we complete this section on how to add spins or add angular momentum, like two particles, the particle may have a spin and an angular momentum simultaneously. What is the resultant angular momentum in that case? Or two particles, one spin, the other spin, then what's the sum of the two spins are there? Now, so this problem here, consider a three-dimensional vector space spanned by an orthonormal basis, cat 1, cat 2, cat 3. And he writes some superposition state is this one. Notice that the component in front of cat 1 is I, the unit. This is the imaginary quantity I. The quantity in front of 2 just happened to be a -2. It could be any number. But, well now, any number such that if you form the inner product of alpha with itself, it should come out to be 1. And same with beta. Beta here then is has cat 1, cat 3, whereas the component in front of cat 2 here must be 0. That's why it's not there. So A is to construct then, if this is the vector A, what is the cat? I'm sorry, if this is the cat, what is the bra corresponding to that cat? The bra corresponding to a cat is to turn the arrow from right to left and change all the complex numbers. You take the complex conjugate of them, but the rest of the regular real numbers are written as they are. So let me just go on and say, the cat for this one, the bra for this one will be -I, bra 1, -2, bra 2, plus I, bra 3. That is the bra alpha that he wants you to construct this bra. And the bra beta here will be the bra beta. You turn the arrow to the left. That would be -I, bra 1, and +2, bra 3. That's the bra beta here. And then find the inner product of the two, go on in that. And then find all 9 matrices of the operator of bra alpha with bra beta. I'll give some hints on how to find that. But you will find that this is going to be a square matrix, okay? All right, I want you to spend some time absorbing this material. Play this video over and over as many times as you need, and also read through the content material that I've given here. And let's now get this additional portion understood. Once we get this portion here, then I'll give the next quiz. About 2 weeks from now, the next quiz will come, okay? All right, dear guys, I'm through for what I wanted to give today. Have a good day. Bye now.